Okay, welcome everyone back. This is our last seminar this term, and we are very happy to have Taro Kimura from the University of Bourgogne from France, and he's going to tell us about some aspects of supergroup gauge theory. Please take it away.
Okay, thank you for the introduction, and yeah, it's my great pleasure to talk at this seminar series. Yeah, so I have joined some of the seminars before, and yeah, I feel it's a really nice feeling, and yeah, I want to give a similar stuff. So, okay, so today I'm going to talk about this some aspect of this supergroup gauge theory, and okay, based on several recent works. So yeah, I'm going to talk about the supersymmetric supergroup gauge theory. And in that sense, we can discuss some natural supergroup generalization of a lot of nice properties of the supersymmetric gauge series, like instanton counting, Perturbation functions, and brain dynamics and cyberpin geometry, and so on. And also, I'm going to talk some possible connection to the topological string realization, and also this connection to the integral system, like this gauge beta correspondence. And also, I want to discuss some realization of such supergroup gauge theory using some intersecting defects in a bit complicated situation, but yeah, I want to mention a possible realization. And okay, so this talk is based on some several of my recent works. And for example, yeah, my work with this Vasily Pestun and Henyu Chen, not only, and also the Sugimoto, Yuji Sugimoto, and also the Fabrizio Nieri, and especially the last one appears in the last Friday. And recently I wrote up my recent the habilitation thesis, and then some of my today's contents are summarized in this thesis. So that if you're interested, so yeah, please check it. Okay, so then okay, so let me start some motivation and some background of this study. Okay. Okay, so today I'm going to use this handwritten type presentation. Okay, so let me start with some overview. So I'm going to talk about this supergroup gauge theory, and okay, so supergroup gauge theory, and for example, in particular, so for example, we can think about the supergroup Yamil theory. Okay, and okay, for example, let's think about the gauge group. Okay, in my presentation, so mostly I focus on this, unitary type supergroup gauge theory. Of course, we can think about them as OSP, but okay, so for the moment, let's think about this U-type gauge theory. And okay, there, Yamil's Lagrangian is okay. This, and the specific feature of this is that okay, so it's almost same as the usual Yamil's action, but now we have this supertrace structure. So this is a really specific to this supergroup gauge theory. So this supertrace gives a natural king form, and so this supertrace. Otherwise, we cannot make the Lagrangian gauge invariant. So in that sense, we should take this supertrace. But so due to this supertrace structure, so this is written like this. So since this supertrace is with respect to the graded vector space, so if you want, you can decompose like this. So F, and plus 2G, FF. Okay, so let's say this trace is with respect to some positive sector, and this trace is with respect to the negative sector here. And then so you realize that, okay, it has the problem. For example, that if you look at this bird, so this is given a wrong sign. in the sense that, okay, this has a wrong sign for the kinetic term of this gauge field. So in that sense, okay, so immediately, so this gives rise to some problem. For example, since you have a wrong sign for this kinetic term, so the spectrum is not unbounded for this supergroup theory. And also, so similar stuff is, for example, this theory is non-unitary, and but this kind of behavior is understood from okay, since if you think about the supergroup case theory, so you should have a fermionic spin one field. So that means, that actually gives you the violation of spin statistic theorem. So from this point of view, so this Lagrangian may have some problem, but I'm going to discuss okay, so some nice non-perturbative aspects of this this supergroup theory. Okay, so let me just write some spectrum. Unbounded, non-unitary. Yes. Okay, but okay, so let me discuss some observation for this gauge series. So this structure. So actually, so we can, okay, this is just a, the gauge theory having a supergroup structure, but it has several nice realization using, without using the supergroup structure. For example, one of them is, so this theory is interpreted as some specific specialization of quiver gauge theory. So quiver realization. So in a sense, okay, the rough idea is that, okay, so we have some gauge field. So, but now since we have a so supergroup structure, which is a graded vector space, based on the graded vector space. So we have some block matrix structure in the sense that, so typically, so we can write some 2x2 block matrix structure. And then, okay, so for example, the first part basically correspond to the, okay, so some G plus part, G minus part. Okay, so my convention here is that this G is having G, okay, so it's not equal, but plus and G minus here. Okay, so typically, for example, the U n plus and minus contains a UN plus, UN minus. Okay. And okay, so this is a block diagonal part. And then of diagonal part has a structure like okay, G plus cross G minus, G plus cross G minus. Okay, I think in this convention, okay, so that means diagonal parts are basically usual gauge group of UN plus and UN minus, and of diagonal plays a role of the actually so bifundamental representation of this G plus G minus. So yes, so from this point of view, okay, so especially so these guys are bifundamental. And okay, block diagonals ones are usual gauge degrees of freedom. Okay, so then from this point of view, so we may interpret this supergroup gauge theory as some specific specialization of the quiver gauge theory. So we have basically two gauge nodes, G plus and G minus, G minus. And then now we have two kinds of the bifundamental degrees of freedom. So we may draw these two bifundamental degrees of freedom. And okay. So actually, so this is, if you want to interpret it as an one hot quiver. Yes. But of course, since we are now talking about the supergroup theory, so it's of course different from the A1 Hart-Kruger gauge theory in the usual sense. So, for example, that we may assign coupling constant, say for example tau. So this is okay complexified coupling. But now, okay, so the point is that okay, so we are having this coupling here and here. So in that sense, so okay, if you interpret this structure from as a Kuiper gauge, special kind of the gauge theory, Kuiper gauge theory, so that implies that okay, for the second negative part of the gauge node, so you should assign this some specific coupling constant here. So okay, so if you want, you can define this as a tau, okay, tau plus, and this is a tau minus. But we should impose a special condition in the sense that okay, so this tau minus should be minus tau plus. So this is a supergroup condition of this from this point of view. But of course, for the physical theory, so we should assign a coupling constant. Okay, so let me write. So the physical condition is that for this complex coupling is that the imaginary part should be positive. So this is corresponding the right sign of this kinetic term of this EM's action. But of course, if you impose this supergroup condition, so at least one of these must violate this physical condition. So in that sense, okay, this supergroup gauge theory is interpreted as some unphysical parameter slice of Kuiper gauge theory, for example. And okay, so let me just.
I thought the way these things arise in string theory is that you actually gauge fix the supergroup symmetry. So in some sense, it's a formal symmetry. You can organize things as a supergroup. But what actually happens is that upon gauge fixing, the bifundamentals, which would have been ghosts, become ordinary matter because they were super.
Yeah, yes.
And so the theory is really actually an ordinary Kuiper theory with ordinary kinetic terms. But you know, should you want, you can think of it as originating from gauge fixing some supergroup symmetry when it really doesn't matter.
Yes, yes. So actually, so this is just one aspect of this, okay, how to see this supergroup case theory. And I'm going to explain, so for example, this kind of picture is consistent with other approach to this supergroup case theory. For example, we can see the nice, for example, brain picture from this point of view, or some connection to the, okay, so this also gives you the nice cybergrid geometry picture, for example. Yeah, I'm going to explain that. So this actually gives you the nice explanation of this supergroup theory. Yeah, of course we have a lot of ambiguity or some saturation for supergroup, but yeah, for the moment. So let me start with this picture. Okay, so let me just remark that this kind of argument was discussed by Dijkgraaf, Heinrich, Jefferson Buffer. So it's almost 5 years ago, but so they discussed this kind of interpretation for this supergroup theory. And okay, so this is just about the coupling constant, but this is about the Yamil theory. But this kind of similar argument is applicable also for example, Chern-Simons theory. And in that case, okay. There's no Yamil's coupling for Chern-Simons, but instead you have a Chern-Simons level, which plays a role of coupling constant. And in that case, okay, so you similarly have 2 gauge nodes and 2 level Chern-Simons levels, but you should impose okay, so negative part of Chern-Simons level should be the minus of a positive part, for example. And this actually matches the situation of this ABGM theory. So in that sense, okay, okay, so for example, the Chern-Simons case, so we have ABGM theory, which is a U, for example, UNK. In general, it may be different. So in that sense, okay, for example, if you look at the Perturbation function of this ABGM theory, so it looks like the super group generalization of the Chern-Simons theory. So in that sense, this ABGM theory may be interpreted as some supergroup version of the Chern-Simons theory. Okay, and okay, so this is about the coupling constant and also Chern-Simons level for the Chern-Simons theory. But I'm going to talk about okay, so I'm going to talk about this n equal to general version of this theory. And in that case, okay, so we can similarly think about instanton counting and Laplace Perturbation function and so on. And in order to write down this Perturbation function, of course, we need this omega deformation for this theory. And okay, so I'm going to explain this. Okay, if you turn on this omega deformation, so you have this epsilon 1, 2 parameter, or yes, for this positive node. But in that case, this negative node, effectively, so we have a minus epsilon 1, 2. Okay, this assignment is naturally derived from the instanton moduli space of this supergroups case. And then, so yes, so if you want to think about the instant counting for this supergroup scale theory, so positive node is of course same as the usual theory. But on the other hand, so the negative node, so you should assign as a negative omega deformation parameter. Yes. So okay, I'm going to tell you so why you have such kind of structure. Okay, yeah, from this point of view, for negative side, so all the charges should be the opposite to the positive one. Okay, so then, okay, this is Kuiper realization.
Why is that?
Sorry.
I mean, again, I thought, so it depends which question I mean, you can ask some question that you decide, but the supergroup theories that arise from string theory are not like this. You would not do that. You would assign the same sign of epsilons for both. Because they're just, they really actually are ordinary quiver theories. They're not any different.
Yeah. Okay, so why you have this plus minus epsilon 1, 2 is, okay, of course, I'm going to tell you. So especially from if you think about the supergroup generalization of the instant modular space, so such kind of structure naturally comes out. So, okay. Okay, honestly speaking, so, okay, at this point, I don't have a precise, rigorous derivation of this plus and minus epsilon 1, 2, but so okay, if you assign this positive and negative omega deformation parameter, so all the arguments are consistent. So then I expect that this assignment is plausible at this point. Yes.
So the supergroup realization I have in mind is, which is in one way, one or another way, related to say, string theory on a conifold singularity, where we know that the theory develops this kind of if you take a D0 brane, you bring it to the conifold singularity, say in type 2A string theory, it fractionates. And at the singularity, we know that it's going to get a quiver gauge theory description. The theory does have a sort of formally supergroup symmetry, but all they're both ordinary gauge theories. So you would not say that. In fact, they preserve the same kind of supersymmetry, that you're not flipping any kind of orientation or anything like that. So in terms of omega background that you put it on, they see the same space with the same orientation. You would not flip the sign of epsilon. Again, you can ask a different question, should you want to get something else, but the things that arise from string theory with supergroup symmetry would not be like that.
Okay, I see. Yeah, okay, so from my point of view, so I'm going to explain why this is a natural assignment of this on the background. Yes. And okay, so this is one quiver realization of this supergroup theory. As I said, okay, so if you embed this supergroup as in quiver gauge theory, so you should assign, think about some unphysical parameter regime. Okay, so then let me then discuss some, a possible brane realization. Yes. Yeah, probably. So it's related to your question. So, okay. So of course, usual UN gauge theory is realized as a stack of these branes, usual D branes. So this is just a stack of n. Okay, so I don't specify dimension at this point, but branes. And okay, so we think about the supergroup theory. So the one realization is given by this paper by this Okuda Takuyanagi. So their proposal was that, so using so-called a negative brane, or sometimes called a ghost brane. So for example, we have n plus, okay, so let's call it a positive brane. So this is so same, okay, this is a usual brane. And then negative, or sometimes also called a ghost brane. Paper by Okuda Takuyanagi proposed okay, how to think about ghost branes. And let me remark that so this ghost brane or negative brane is different from the anti-brane. So okay, I'm going to tell you in which sense so they are different. But the negative brane is not anti-brane. Okay, but okay, so if you start with such a negative brane, so we can similarly think about a lot of the brane realization of this gauge theory. So for example, okay, so in my talk, I'm going to focus on this n=2 analog of this supergroup gauge theory. So from this point of view, let us apply the standards. So this Hanani-Witten type configuration. So, okay, so this uses a usual NS5 and also several, okay, so this suspended usual branes and also this negative branes. Okay, it depends on the dimension, but for example, the 4-dimensional theory is realized using D4 brane. And then in order to emphasize this is a positive brane. Positive brane is a usual brane. So let's put plus here. And then this is negative brane, so D4 minus. And the number of branes, of course, n plus and n minus D4 branes. So this is a natural realization. And okay, so let me, okay, for the moment remark that this configuration is still BPS. So because if you think about the both positive brane and the anti-brane, so it's going to be the non-BPS. So due to this tachyon condensation, something like this. But since this negative brane is not same as anti-brane, so that we can keep this BPS configuration here. Okay, so this is a natural realization. And okay, let me explain. So the previous realization, I mean the quiver realization. Why? Okay, how this picture is related to the previous quiver realization. So okay, so we have NS5 again.
Can you define these before we go with NS5 branes and so forth? Can we do these negative branes in flat space? How do you define a negative brane in flat space?
Okay, so in that case, of course, originally, so the in order to define this brane, so you have to, of course, specify what is the boundary condition of this open string, and you can assign a Champeto factor sample. And the original, of course, definition of this Okuda Takuyanagi was that okay, so this paper so discuss the usual flat space, and then put this negative brane. solution for this boundary condition. And then typical point is that the specific point is that you can assign a Champeto factor. And then in the usual case, Champeto factor is, for example, if you think about the stack of n-branes, so Champeto factor takes a value in a Cn, I mean, n-dimensional vector. But if you assign this specific boundary condition, so this Champeto factor is going to be the super graded vector space, C n slash n plus slash n minus, for example. And then you can construct such a boundary condition from this worldsheet perspective. Yes. So okay. So okay, I'm going to explain how this negative brane realization is related to the previous quiver realization. Okay, this is a interpretation, but if you think about such configuration, so this is actually the brane realization of this theory. This is a cyclic quiver. A1 hat quiver. Yes. And then, but in order to realize the supergroup theory from this quiver gauge, cyclic quiver gauge theory, so you should tune the coupling constant. So, for example, the first coupling is basically correspond to the distance between two NS5 branes. So this gives you proportional to the coupling constant. And the other coupling constant is corresponding to the this length. So you have a total length, cyclic length, and so this interval, or if you measure the distance from inside or outside, so this gives you the the coupling constant for the first node and the second node here. Okay, of course, this is a usual realization of A1 cyclic quiver, but the point is that this tau minus should be tuned to the tau1. Okay, so the point is that so you should tune a tau1 to minus tau0 here. So this is a kind of interpretation, but originally you have, for example, in this picture, so you have two external, two D4 branes outside of this NS5 brane with the length tau1, tau minus. Sorry, this is a convention is not good. So mixing the convention. Tau minus is Okay, so now the length of this tau minus is measured with this external side, and this is having a positive length, but this gives you the analytic continuation or interpretation of this figure. And if you have a negative distance, so this is interpreted as so originally these D4 branes are living on outside, but after this analytic continuation, so this external one is flipped into the inside of this NS5 branes. So this is one possible interpretation of how to think about the negative coupling constant. And then if you after this analytic continuation, so these external branes are converted to the negative brane. Okay, so this is of course this interpretation, but this is also consistent with other pictures. Okay, and for example, from this figure, so we can understand we can learn some more aspects. For example, yes.
I'm not sure if I understood the claim.
Sorry?
So how do you see the relation between the T minus and tau minus and tau plus from the picture?
Sorry, what do you mean? So so the tau minus is essentially the length of NS5 branes. Sorry. Originally this horizontal direction is cyclic. So in order to realize that this cyclic quiver, and then okay, I think okay, this picture is not good. Okay, so we have a cyclic direction, and then okay, so I think this. Okay, so if you look at this picture from this direction, so you may have roughly speaking, you have such kind of the configuration, and these circles are interpreted as NS5 band. You have two NS5 bands. And okay, now roughly speaking, so this length is tau plus here, but you have a total cyclic length. And so original picture, so you have tau plus and tau minus is going to be the total length of this cyclic direction. So this is okay, the meaning of this picture here. Yes, and okay, so okay, right. So it's a bit difficult to draw the nice picture, but originally this tau minus is measured as measuring so external. Okay, so it's possible to measure the distance of NS5 lane on inside or outside. So since this is a cyclic, so and but if you convert the tau minus to the, for example, negative value, so this current interpretation is originally this measure outside. I mean this direct. I mean outside of this NS5, but minus means so the I'll say yeah, measuring distance from inside.
I have a question. Yeah. What's the origin of these brains in M theory? How do we know they exist? What corresponds to them in M theory?
Okay, so I think it's nice to explain this picture from the. Okay, I'm going to shortly explain the subwritten geometry picture. So then yeah, at this point I'm going to tell you some interpretation. Yes. Okay, of course, yeah, okay, it's just interpretation. I'm not sure so how this is precisely related to this M theory picture, but yeah, at least
my question is whether these objects actually exist, right? Whether they exist as string theory objects. So the fact that you can write down something on the world sheet does not mean that this object exists non-perturbative. To convince me that it exists non-perturbatively, you would have to show me how to construct it in M theory. Then I'd be convinced that it exists. Otherwise, it's something one can write down on the world sheet, and maybe after some thinking we could decide that there's something wrong with it. If you can show me a simple construction of the object in M theory, either as originating in an M2 brain or an M5 brain, I guess maybe then I would believe it.
Okay, so yeah, I'm going to explain. So geometric engineering of this picture. So then I'm going to explain what is a possible realization from such a string theory geometry and the topological string. So okay, yeah, okay, I'm not sure. So this okay, I don't say that at this point I can explain this. So rigid.
Do we have any process at all by which two BPS objects could annihilate and disappear in any theory at all? That they really actually exist, that you can, or that you can produce it by moving around in a moduli space, or
yes, I'm now explaining this part. Yes. So okay, now we have this picture, and then from this picture, so we can discuss a possible brain arrangement. And for example, from this picture, so we can discuss okay, so we have such deep brains, and then if you want this, you can assign some additional degrees of freedom like this. Okay, but at this point, so actually, so we don't do anything, but we can gauge in this configuration. So then gauging means gauging so bottom to default branes. In a sense, okay, so we have okay, so external default branes are fixed at this point, but so since we are now gauging bottom two default brane, so this actually enters as a Coulomb branch description. Yes, but okay, so as you said, so essentially, so these negative branes having some opposite charge to the positive one. So in that sense, okay, if you further tune in this Coulomb branch parameter for especially for these bottom two ones, so it's we can go to this configuration. But of course, this is tuning. So Coulomb branch parameter, which is a Coulomb moduli here. So then, of course, after this iteration, so this there's no negative brane, and from this picture, so this gives you the okay. Now this is SU n plus SQCD with 2n minus Fribus. Okay, so okay, so that means okay, so originally we have a supergroup structure, but if you okay, this, for example, this geometry, that geometric manipulation implies that okay, so this supergroup gauge theory is more or less connected to this SQCD with a specific Fribus. And that means if you think about some specific point of the moduli space, for example, in this Coulomb branch, so this may describe some aspect of this supergroup gauge theory. And okay, one comment here is that you can directly comes to the final picture just by taking decoupling. The negative node, which means tau minus to infinity.
Has anybody studied non-perturbative stability of these things?
No, but that means okay. So I'm going to discuss this, for example, this instant accounting and the spectrum function.
You don't have to think about instantons. Let's just study quantum mechanics.
Yeah, okay, yeah,
of course, yeah, of course, sense?
Yeah. Yeah,
it doesn't feel, to me, it feels deeply unphysical, but I could be wrong. But it seems like there's some calculation one should do to actually show that this makes sense.
Yeah, yes. Of course, I want to demonstrate, okay, starting from this instanton calculus and then localization, the necrospectrum function, then taking, say, epsilon 1 to 0 limit, taking the classical limit of this stuff, and then we can derive this Savarin geometry. So yeah, we can derive such kind of picture from such.
I guess supersymmetric quantum mechanics is part of Nekrasov's calculus, right? So you will indirectly answer my question because you will have some quantum mechanics of, I suppose, super D0 branes within it, right?
Yeah.
Okay. All right. Great. So let's see.
Yes. Yeah. Yeah, I'm going to give you some more details about this. Okay, yes. So anyway, so I want to demonstrate that so originally, so we have a supergroup theory. It sounds a bit mysterious, but so this has a several realization using a non-supergroup gauge theory. But so using thinking about the unphysical parameter regime or some special point of this Coulomb branch, for example. And okay, so let me first here remark that so okay, now we have so such kind of the stacked of D-branes, but now we have the two kinds of the D-branes. So in that sense, okay, precisely speaking, so we should be careful about the ordering of this positive negative branes. So what I mean ordering. So ordering means so we have for example, if you think about the SU2/1 theory, so of course, natural realization is something like this, but this is, so it's possible to have to realize a different orientation or different ordering, for example. So so from this point of view, so it's not clear that how to show this equivalence, but actually, so we can use so similar, so topological vertex formalism for such supergroup theory, and then in that, so from this point of view, we can show that the partition function does not depend on this ordering of this positive negative planes, and this has a cross connection to the some structure of this supergroup, in the sense that so we have, so since this brain picture is related to the so you can read off the what is the simple root structure of this corresponding case theory, in the sense that so this for example, the leftmost figure corresponds to the thinking diagram this type, and this type. So actually, so the supergroup case, so the thinking diagram is not unique. So given, for example, in this case, we are talking about SU2/1, but so we have 3 equivalent thinking diagrams, and so this is so that means so 3 possible decomposition into the simple roots. Okay, the rule is that now we have so you have red. So in that case, you assign a usual node. But if you
this
have
ordering doesn't mean much here, right? Because these brains can go around each other.
Yes. So okay, but in this case, yes. So of course, from this point of view, so the ordering is not important. But for example, what I mean is that I'm going to tell you the topological string and topological vertex calculation of this partition function for this supergroup case theory. So in that case, we can think about several possible, for example, the assignment of the topological vertices, and in that case, so from the first expression, it's not obvious that these 3 configurations are equivalent. But of course, from the brain point of view, so these 3 configurations should be the equivalent. But so from this, so from this equivalence suggests that implies that so we have a 3 possible thinking diagram for example, SU2/1. Okay, so yes. And next I'm going to briefly explain that from this brain picture, so we can read off the, for example, Savarin geometry. So from this brain picture, so we can read off such a property. And so for example, such a Savarin geometry of the supergroup case theory was originally discussed by this diagram and here Jefferson buffer. And the observation is the following. So we have a pure, for example, the pure SUN. Okay, so in this case, we have such Savarin curve. Okay, so this is SUN, pure Yamis. And so this right-hand side is actually interpreted as a characteristic polynomial of this Higgs field. Okay, this phi is a fixed field or this vector multiplet. And from this point of view, so since we have the characteristic polynomial, and of course this phi is okay, the determinant is of course with respect to this SUN structure. So then it's natural to try this superdeterminant if you have a supergroup structure. And of course, this is superdeterminant. So this is going to be the ratio of a plus ratio of two polynomials. This is n plus and minus. Yes. So then this is a natural candidate for this self-evident curve for the supergroup. So okay, so we can see that this is consistent with a previous argument. For example, the SUN SQCD. So we have discussed that so this supergroup gauge theory is up to the duality chain. So we can get SQCD. And in this case, self-evident curve is having following form. Of course, we have several possibilities, but let's try. This form. Okay. And okay, the previous observation was that okay, so the number of flavor is like this. The flavor symmetry is related to the rank of the negative bird. So from this point of view, so we tune so mass parameter. And the point is, okay, so then the point is that from this point of view, so this actually the position of this external D4 planes are related to the fundamental mass parameters. But from this configuration, so we should have a pair of the fundamental masses. So since originally we have such a horizontal D4 planes, so then we have a pair of fundamental mass parameters. Okay, so then from this point of view, so let's try NF equals to 2n minus, and then the mass parameter is actually M1, M2, M2, and something like this. So given a pair. Then, so originally, so we have the square root in the denominator, but since we have the pair structure, so then this ends up with the numerator is of course same. But this is going to be the n minus x minus m f if you want. So then from this point of view, so if you identify the denominators as a negative contribution of this superdeterminant, so if you want, so you can identify this. And in that sense, okay, so the denominator is of course the parameterized in the Coulomb moduli for the positive node, and the denominator parameterized is the Coulomb moduli for the negative bird. And of course, this is also consistent with the previous argument in the sense that okay, so in that sense, okay, so sorry. Okay, so it's not good observation, but anyway, currently the mass parameter is interpreted as a negative Coulomb moduli here. And okay, so I don't explain details, but so such a consistency of the cyclic geometry is also observed from this A1 hat cyclic river description. In that case, the self-evident curve is going to be given by the elliptic function. So for example, this left-hand side is going to be the elliptic function. But if you assign so this supergroup condition, saying tau plus minus supergroup control for a tau plus minus. So we end up with such kind of actually constant picture for subroutine geometry. All right. Okay. So this is just a brief overview of this supergroup theory, and then next I'm going to talk about so what is an instanton modularized space for this supergroup gauge theory. Okay. So let's think about the super instanton counting. So this is mostly based on my paper with Vasily. Okay, so what is a fundamental idea for this? So of course, in order to derive the Nicholas separation function, so we should clarify what is a ADHM modularized space, instant modularized space. And in order to that, of course, we can use this ADHM construction of the instanton, but we may need some super generalization. The observation here is that, okay, the first point is that this ADHM so actually ADHM construction is interpreted as a T duality, or more mathematically, so it also interpreted as a Fourier-Mukai transformation. And the point is that okay, so we are interested in, for example, the K instanton in UN theory. Okay, so this is of course a usual gauge theory stuff. But okay, so let's think about the 4 torus for the moment. And this is actually T dual to the N instanton in UK theory. But after this T duality, so we will have a dual torus here. So for example, the radius is given by R. And on this side, so this dual torus radius is, for example, denoted by R check. And this is actually 1 over R here. So we have a converting radius here. And the nice thing here is that, okay, so we can take, for example, R to infinity limit. So then this torus is going to be the R4. But on the other hand, the dual torus is going to be just a point. I mean, just a 0-dimensional point here. And okay, so the brain point of view, of course.
What's the genus of the Riemann surface?
Okay, so this torus is usual.
No, not the torus, the Seiberg-Witten curve.
Yeah. Okay, here. Okay, so for example, in this case, genus. Okay, so in this case, of course, this curve is equivalent to. So this is a SUN with several matter contents. So this genus is at this point n-1 related to the rank of the gauge group. And from this point of view, so this rank, genus of the subrobotic curve is determined by the rank of the positive gauge node, positive part of this supergroup structure. And since this rank, okay, this genus is determined by this polynomial here. So since this is okay, the numerator is a polynomial of degree n. And if you want us this, yes, and then okay, so this, okay, so interpretation is a bit yeah, actually the peculiar, but so in addition, so you may have some pole structure here. So this is also related to the denominator. So this singularity is related to this denominator here. So in that sense, okay, so originally the supergroup should have a symmetry which swaps the positive and the negative part of the, okay, so positive and the negative nodes. But from this point of view, so yeah, that relation is not clear actually. Of course, the symmetry should be the super determinant or the 1 over superdeterminant. But yeah, from this geometry point of view, yeah, such symmetry is not clear here. Yes. Yeah, actually, so yeah, I want to understand yeah, this point, but yeah.
From your brain picture also, this theory should not have such.
Yes, right. So yeah, it's a, yeah. So since we have some negative brain, so then that interpretation is not so obvious. Yeah, I'm going to give you some geometric engineering point of view. Yeah. Okay, so the idea is that, okay, so ADHM. So we have, okay, for example, in a string theory realization, I mean, brain realization. So this, in order to realize this K instanton in UN theory, so for example, we can think about the D4 brain and D0 brain. And after this two duality, of course, the D0, D4 are swapped each other. Yes. But now, so we want to discuss a supergroup generalization of this. And then we discussed that, okay, in order to realize a supergroup theory, so we should use both positive and negative brains. So in that sense, so we may replace something like this, and plus minus here. Okay, that means n plus, okay, D4 plus, and n minus, D4 minus. So we have n plus positive brains, and minus negative brains, something like this. And okay, so then, so after this two duality, so we will have n plus, n minus. Okay, but okay, this ADHM construction is actually, so we have a gauge group rank and instanton number, but these two are actually equal footing or converted to each other from this T duality. So this is a ADHM or just a T duality. Okay, from this point of view, so it's natural to think about, yeah, I think this is related to the Mina's previous question. I mean, so super D0 instanton. So it's also natural to think about the K plus, K minus, D0 plus minus brains. Of course, this means K plus, K minus, D0 minus here. And of course, after this, so we also get the dual side of the story. So we will have the U K plus slash K minus symmetry. So then, okay, so we have a -3. So equal footing situation, the gauge group rank and the instanton number here. Of course, originally this rank and the instanton number are originally coming from the number of the D brains. So then, yeah, so this seems more natural from this point of view. Okay, so then from this point of view, if you think about the instanton counting or instanton modular space for this supergroup, so it's natural to think about such, I mean, K plus minus situation, instanton. And okay, so from this point of view, so in, okay, actually the starting point of the ADHM construction is that, okay, to just define some vector spaces. So, which is related to the, originally, so we have a so-called N vector space and a K vector space. So sometimes it's called a framing vector bundle and framing space and the instanton space. But of course, this is going to be replaced with a graded vector space. Both of them. Okay, so this is a natural setup of this super ADHM construction. And of course, these vector spaces are interpreted as a Chern-Payton factors of this D0 plus minus, D4 plus minus. Yes. And of course, this is a Chern-Payton factor. D0 plus minus and the D4 plus minus. Okay. Then, okay, so let me briefly summarize what is a, okay, so since it's a bit confusing, so we may have a usual instanton and a negative instanton, for example, since we have the D0 minus plane. So in that sense, so let me summarize some terminology in the sense that, so we have a usual instanton. And it's okay, also possible to discuss anti-instanton. But also think about the negative instanton. So negative instanton should be different from the anti-instanton. And in general, so if you want, you can also discuss the anti-negative instanton in general. So we have 4 possibilities actually. And the instanton, anti-instanton are actually distinguished looking at so self-dual or anti-self-dual. So okay, of course, it depends on the convention, but okay, in my case, so let's assign ASD condition for the instanton, and anti-instanton is actually the self-dual, so having the opposite orientation. But actually, negative instanton is again anti-self-dual, and the anti-negative instanton is having a self-dual. So, okay. And okay, so this explains why this negative plane does not violate this BPS configuration, because so if you have an instanton, anti-instanton, so since we have both ASD and SD, so in that sense, we cannot, okay, so this actually ends up with a non-BPS configuration. But since instanton, negative instanton, both have ASD configuration condition, so then that actually can keep the BPS configuration. And for example, so we can discuss a topological instanton number, I mean, instanton charge here. And we assign a usual instanton, the positive instanton charge. And anti-instanton, of course, have a negative charge. And the negative instanton also have minus, negative. And the anti-negative instanton may have positive instanton charge here. And if you want in this context, instanton is realized as a D0 brane, a D4 brane. So the brane is, okay, this is a usual positive brane. And the anti-instanton is realized as anti-brane, but anti-positive brane. And then the negative instanton is going to be realized as a negative brane. And anti-negative is going to be the anti-negative, something like this. Okay, so this is a kind of the table of the instantons, and also that is what is the negative and the anti-instantons. And okay, so as I said, so this D0 plus and the D0 plus minus. So this is going to be the non-BPS, which is going to be unstable. But the D0 plus, D0 minus is still BPS. So actually, so it's known that from this ADHM construction point of view, so we are, of course, we can also discuss this anti-instanton just by flipping the orientation, but we cannot discuss the both of instanton and the anti-instanton at the same time. So this is related to the, okay, so the BPS, I mean, actually, so this violates the BPS. Okay, so since this is a ASD plus SD, so this is a ASD, both of them are ASD. Okay, so this is a setup. And then actually, so starting with such configuration, so the ADHM construction itself is going to be straightforward. Since the, okay, different point of view, for example, you may have ADHM equation, but this is just coming from the supersymmetric vacuum condition. But in this case, we can actually have a essentially same description. So so for example, if you want, you can write down ADHM data or ADHM variable. So you can apply the same argument. For example, the so-called B matrix.
I'm sorry. What is the motivation of introducing these brains? Like, which problem do we solve that we didn't have some other solution for?
So you mean motivation for the negative?
I mean, if you think of just, yeah, would thermodynamics of these objects make any sense at all? Like forgetting about supersymmetry?
Okay, so the property of this negative brane is that, okay, so I think it's nice to explain a bit what is the difference between anti and the negative brane. So anti-brane has, for example, negative charge, but they're still having a positive mass.
Why wouldn't the energy of the vacuum be unbounded from the below in presence of such things?
Yeah, exactly. So if you have such a negative stuff, so the energy is not bounded. Yeah, so this is actually, I explained in the beginning, so that if you have such a structure, so we may have unbounded structure. So in that sense,
doesn't this destabilize string theory if we have it, if we have such things?
Yes. But
what are we gaining by introducing this?
Yeah, so, but still, okay, for example, if you have such a negative brane, so the spectrum is not bounded, but still we can think about, for example, the equation motion, and also this instanton is actually a solution to the equation motion. And okay, so that we don't have a digit bounded spectrum, but we may possible to discuss, for example, the complexified saddle point or equation.
But we think of string theory, and at the end of the day, it's a physical thing, right? I mean, string theory has these objects. Like M theory vacuum is unstable, string theory is unstable. Then we can all just go home. I mean, if somebody thinks that these are physical, I think we should be going and trying to shoot them down, because this is not a good thing.
Okay.
I mean, so we're throwing away consistency of string theory for very little, for what I can see. So I think the most interesting thing is, like, explaining why they don't exist, as opposed to trying to get a little bit of math from their existence. So I just don't get it.
Okay. So from this point of view, so of course it sounds like unstable and unhealthy, but actually, so for example, we can discuss this supergroup gives you some effective theory of some intersecting defect, for example. So starting with some higher object, and then if you think about some specific configuration, so this is supergroup structure gauge theory gives it some effective description.
Well, I still haven't gotten convinced that these objects make sense. The way you're, I mean, I do believe the supergroups arise, just not this way. I mean, if you wanted to get this root structure, right, you just take, the conifold singularity, or the various m/n conifolds. I guess, many people have studied this, including Miroslav. That's going to give you all the, the interesting, the fact that the, GMN/supergroup, GM/n supergroup has, different thinking diagrams. But, this is obvious in that picture. So, what else am I? And you can, show rigorously that these theories have, very fancy versions of quantum, whatever, symmetry. Why are we going this route?
Yeah.
Even if you love supergroups.
Yeah. So I want to explain, for example, I can give you some connection to the Miro's construction of, for example, the corner vertex operator. And so if you think about some specific singularity of this Calabian, so you can see some supergroup structure. And actually, so this story is naturally, so we can see the natural connection to such a singularity from this negative brane picture. So, for example,
are you going to explain this? Because I think we understand other ways how such things arise. So maybe, okay, your explanation better be better than the other ones.
So sorry. So it's a very slow, but okay. So the time is very going. Running out. So let me be quick for this point. So anyway, so we have a DHM, and then. Okay, let me just conclude this part. So this, for example, this B matrix is just as usual. So this is, for example, K vector space, a map from the K to K, and we may introduce similar. So we may have such ADHM variable. And if you want, so this is naturally described as some quiver diagram, which is called the ADHM quiver if you want. So B12. But the point is that this vector space Kn are graded vector space. So then, so B12 ij is going to be the supermatrix here. But okay, so everything is formally parallel to the standard one. So the only difference is just this framing vector space and instant vector space is just a graded vector space. So then from this point of view, we can think about the ADHM moduli space using the usual. Actually, so since we have the same ADHM quiver here, so that we have the same ADHM equation, which is a corresponding moment map assigned to this this quiver variety in general. And if you want to, you can interpret this as some backend configuration for this difference. Okay, so then okay, let me quickly give you the why, explain you the why. So you should assign a positive and a negative epsilon parameters. So this is a crucial point here. And okay, so you should have the ADHM moduli space. So this is, for example, NK. Originally, this is a moment map equation with a hyperkiller quotient, if you want. But originally, this definition may have a singularity. So this is going to be, it's nice to regularize this with, so if you want the simplex quotient or GIT quotient, but the complexified gauge group quotient anyway. But in this case, you should have the so-called stability condition. And the stability condition is that, okay, so in order to assign a stability condition, so for example, we should replace the original ADHM equation with, okay, I don't explain what is this new definition of this, but originally this condition equation contains this equation, but so this is replaced with some, okay, so this is kind of the, resolved version of this ADHM equation. And this zeta parameter has a natural interpretation as, for example, non-computative parameter or something like this. And okay, so but this zeta parameter should be non-zero here. Okay, so then actually the stability condition is given by like this. So we have this instanton vector space K, but this is actually spanned by right here. So this is for zeta is positive, but instead if you have a negative zeta parameter here, so instead you should use okay, this is sometimes called a co-stability condition, but so usually people only focus on this configuration, but since so this is okay, so I'm going to explain as why, but so we should think about both of the stability condition at the same time for the supergroup. Since okay, as I said, okay, originally super case. Okay, so we should replace the ADHM equation. Especially for this blow-up version. So we should assign this kind of configuration, and then this UC is still 0. So in that sense, okay, so the both situations are possible. If you think about the zeta as positive, the negative, positive part is positive, and the negative is negative. That's fine. But anyway, so we should think about the both of stability and the co-stability conditions for this case. And for example, K plus is actually given by B1, B2, and plus. diagrams here. This is diagram here. And actually from this point of view, so we can see that what is the equivalent action on this instant moduli space. I mean, so this is a crucial for this omega background and then omega deformation. Equivariant action. So especially so from this omega deformation, so mostly so we should think about the U1 squared action, so which is originally this SO4, the Cartan part of SO4. And under this equivalent action, so this B12 matrix is rotated as a Q12, B12. So this Q is actually exponential of this omega background deformation, omega deformation parameter here. And the actual point is that since we have B12 for the positive, but the inverse, I mean, so the dagger here. So in that sense, that's a positive sector. So positive instanton should be counted with this epsilon 1, epsilon 2, as usual. But the negative part should be counted with a minus epsilon 1, epsilon 2 here. So this is related to the stability and the co-stability condition. And the physical interpretation is that, okay, as I said, this epsilon 1, 2 parameters are interpreted as if we want the Fy parameter from this superconductor mechanism point of view, and also if we want a non-commutative parameter or the some fluxes. But the point is that, okay, since the negative sector, so all the charges are flipped to the positive one. So then from this point of view, so that we should assign this negative epsilon parameters from this point of view. So actually, so this is a kind of physical, I mean, so just an assumption, guesswork. But so we can see that, okay, if you start with this omega assignment, omega background, so we can derive the cyber-written geometry from the necrospectrum function, the supergroup case theory, and we can also discuss, for example, the connection with the topological string amplitude and so on. Okay, so yes. Okay, so then, okay, so I don't go into the details of this in the class of instanton calculus, but let me then mention a connection to the possible connection of topological string picture.
Hi, Taro.
Yes.
Before you go to topological string, can I ask you something? So like, if you actually considered the Nekrasov partition function as you constructed it, and you do saddle point analysis on it, you should have like some version of the beta gauge correspondence.
Yes.
That will show up. And so my question is, the integrable systems you obtain in that way, are they known in the condensed matter or like integrable community to be things that like they studied, or is it really just some formal, again, kind of like supergroup construction that is going to show up that they didn't study before, or is new, or what do you get?
Yeah. Okay. Yeah. So let me briefly explain this point. So probably I don't have much time to explain this gauge part, but okay. So the answer is a yes and a no. So if you think about some specific situation with supergroups, so that reproduces a non-integrable system. But if you think about different case, so we may also get some new situation actually. For example, the primary example is that if you think about the G super Yamil theory, so we have okay, so precisely this is going to be the Lagrange dual and affine Toda integrable system. Okay, this is a primary example of this relation. And if you think about the G n equal two-star theory, I mean, having an adjoint matter, so it's going to be the G Carogero system, example. And from this point of view, of course, this currently we have so the supergroup structure. I mean, the G is supergroup in this case. And in this case, so we will have, so we can think about the G is a supergroup, for example. So actually, so the corresponding Karojero is actually known in the sense that, okay, Karojero Hamiltonian is written in terms of the root system information and root system data. And for example, the sum of all the possible root vectors and so on. And there is a natural generalization of the Karojero associated to the super root system, which is sometimes called a double Karojero or a super Karojero or something like this. And actually, so we can show that if you start with this supergroup case theory, and then taking epsilon 1 to 0 or NS limits, so we can actually get this double Karojero integrable system. And yeah, so that was done in my paper with Henry Cheng and Anatol Lee. And okay, in this case, so we reproduced a non-integrable system. But the situation is going to be a bit different for SQCD case. So in that case, okay, for the usual SUM case, so if you start with SQCD, so we will have the XXX or XXZ spin chain model in this case. And but in this case, the information, I mean, the correspondence is that, okay, so if you think about, for example, SUM gauge theory, okay, it depends on a 2D picture or 4D picture, but okay, very roughly speaking, so the gauge group rank is related to the size of the chain, number of the sides, or the number of the magnons in the spin chain side. So in this case, okay, if you think about the supergroup situation, so we may have okay, so that what we call the positive and negative magnon. So negative magnon is a bit so peculiar excitation from the spin chain point of view, and I think okay, actually, so we don't find any study in the literature. And the negative magnon is, okay, as this name suggests, so that has some negative energy, if you want. So we have XXX or XYZ, or anyway, so spin chain model. But having positive and negative magnons. So yeah, I think this is a new perspective for this integral system. And of course, okay, but this XXX chain, so this has a usual SL2 symmetry. If you think about the usual single node, I mean, SQCD, and then if you want to think about a much higher symmetry for spin chain, so you should think about the quiver gauge theory. But still, so this symmetry is a usual SL2. And if you want to think about some super symmetric spin chain model, so we should think about the slightly different stuff. So it's going to be some super, okay, so these stuff are related to the S-duality. So we should think about some super quiver gauge theory, something like this. So, okay, so this is not yet, it's not yet known. Okay, is it okay?
Yes, thank you. No, yeah. I mean, I guess like a dual question to Minas would be, I don't know exactly what possible issues would arise from having negative magnons, XX spin chain in terms of stability and so on. So
yes. I think they're having a similar issue. Yes. So we formally read off what is the spectrum from. Okay, so we formally get the Bethe equation for the corresponding situation, and then we can read off what should be the spectrum from this spin chain model. But yeah, as I said, so the stability or unitarity or spectrum boundedness, I think it's gonna be the problematic bit. But formally we can read off such kind of spectrum. Okay, so okay, so then let's turn to this topological string. Okay, so let me explain some what happened for the usual group case, and then let me discuss what should be the super analog. So the primary point is the so-called geometric engineering. So if we want to realize the SUN gauge structure, so we can use the AN singularity. And okay, if you use AN, SUN plus 1 structure. So, okay, so it's expected. So this is generalized to the arbitrary ADE, but for the moment, let's focus on this A-type singularity here. So, for example, if you think about the originally we have a brainwave. So originally we have, for example, such kind of structure. And actually, so we can identify this as a toric wave, toric diagram. At the 2B point of view, this is nothing but a PQ brane. But actually, so we can apply the geometric transition. And in this case, so we may have such structure. So probably not this singularity here. And we can generate this argument to the arbitrary AN. Okay, so then let me give you some discussion about this. So, okay, so originally we have such AN type singularity. And but in general, so you may think about the Taubnut geometry associated with this AN singularity. For example, there is, okay, it's also called a multi-centered Taubnut geometry. So this has a structure like, okay, it's having a Siga type geometry, for example. And okay, but having some singularity on R3 in the sense that so we have S1 and we have some singular point. But of course, if you take the large S limit, so it's going to be Airy space. Okay, so we have n singularities. Okay, or n-centered Taubnut here. Okay, so then the possible situation for the supergroup case is the following. So originally, in order to write down the Taubnut metric, so we can, it's nice to introduce some sometimes called a potential function. And okay, it's going to be the, okay, for the Taubnut, so we have some constant with okay. So the Taubnut metric is written using such kind of potential function. And this xi is actually parameterized in a way as a singularity in this Taubnut case. Yes. But okay, so I think it's better to write this is a +1. The reason why I emphasize, okay, I put this emphasize this is a +1 is that okay, so in the usual case, this singularity of Taubnut is of course coming from the up to the duality chain. So this is coming from the different singularity originally, and in the usual string theory setup, so all the brane has a positive tension. But if you allow the existence of negative branes, so we may have this kind of situation. I mean, and plus, okay, this is a usual, and also -1. So the plus minus is originally coming from the charge of the tension of this difference originally. So this is interpreted as coming from the negative contribution, negative plane contribution, while this is a usual positive planes here. Okay.
Is it singular?
But, yes, sorry.
Is it singular?
Yeah. So and actually, so this is a top knot and maybe singular. But and actually, so if you take the area limit, so basically shrinking all the singularity to the single point. So
sorry, Tau knot is not singular. I didn't understand. Tau knot is ordinary Tau knot with positive contributions is not singular. There are no singularities.
Okay, yeah. So this is not singular. Yeah. So it's called the centered. Yeah. So if you want, it's a position of the H flux if you want. Yeah. Anyway, so
I didn't understand this. With these negative contributions, is it singular?
Yeah. Actually, so honestly, I don't know. Actually, so I'm now explaining some guesswork here, and then probably someone discussed, but yeah, I don't know that this gives you the precise solution to that.
Actually, doesn't this sit inside the metric? I mean, doesn't V multiply the metric? So you would have negative definite terms in the metric. This metric doesn't make any sense.
Yeah. So in that sense, okay. So let me point. Okay, let me mention this point, and okay. So before going to this, so since we have so before going to this, so if you take the area limit. So I mean, all the singular, all these fluxes are, condensate, and then so it's going to be the plus minus and minus here, actually. So in this limit, so we cannot distinguish what is a positive, negative. So what we can measure is just a difference between the positive and negatives. So this is actually related to the argument like so this SUN. Okay, is it really possible? Is it really possible to distinguish these two theories?
Yes, except that if you come near any one of the centers in the ALE space, in the ALF space, the metric is locally flat.
Yeah, right.
And with a negative sign, it's going to be locally flat with the wrong sign of the metric. So
right. So in that sense, okay, so that is related to the. Is it really so? This supergroup theory is equivalent to the usual theory, but with this specific this rank. Yes. And actually, so I think this is related to the Minan's question. I mean, so this kind of non-positive definite function. So it's a discussed like.
I think this is an extraordinarily good argument that these things don't exist. If you did put M theory on this space, you would get in the low energy limit your ghost D6 brane, and clearly the space does not make any sense. You cannot have a sharper argument than that, I think.
Okay, so so this is just very hand wavy argument. So yeah, I don't claim this is
no, it's extremely precise.
Okay, so actually, so this argument is related to the some. So this implies some signature change of the metric. So since we have such a
your Yang-Mills action also when you started your talk, you said there was a term negative trace F wedge F, right? Or so like that's also that problem, right? That like the trace F wedge F term like comes out with the wrong sign from in the Yang-Mills.
Yeah, unbounded, yes.
Right. So, I mean, that's another manifestation of this, I suppose.
Yeah. So I guess this space isn't singular. It just doesn't make sense as a space.
Yeah. Okay. So yeah, let me just give you the remark that so using such a negative.
And actually, all the more the fact that you can make it look like it makes sense at infinity, while it doesn't make sense in interior, which is you could also say at infinity. The metric behaves just like the metric when R4 mod Zn minus Zm. Okay.
Yeah. Right. Yeah, okay, so let me get one single comment. So using such a peculiar potential function, so the one can discuss some signature change. So originally, if you want plus minus 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 kind of the signature, but it may possible to, convert the signature. And this kind of argument was discussed by this Andri, Jefferson Buffer. And they discuss, okay, if you have such a negative contribution, so it may be possible to think about some signature change of this metric. Yeah. And okay, so okay, and okay, this is a possible interpretation here. And okay, so let me then discuss some okay, possible interpretation, another possible interpretation for this resolution. So since we should have this n singularity to realize the SUN in this case, for the usual case resolution. So we have, for example, from the subroutine geometric point of view, for example, originally we have an singularity in the sense that we have extra n's here. But if you resolve this, so this right-hand side is going to be the generic polynomial having several coefficient. Then, so this is interpreted as a determinant characteristic polynomial of this Higgs field here. So this is usual for the SUN for the usual case. And possible, okay, this super resolution is going to be since for the super case, so we should have some ratio of these polynomials. So for example, n plus minus. So since we want to interpret this as a super determinant, so I see n plus. But so we should assign a condition like this. So since we start with x to n singularities, and then for the usual resolution, of course, just replacing the usual with a polynomial. But in this case, so we should replace with some rational function here. But keeping a condition like the degree of n plus and minus having like this relation. So from this point of view, this an singularity is in some sense very related to this n plus and minus singularity, but having a condition like this. Yeah, so this is related to, yeah, so your argument. So if you think about the infinity of this tabula, so we cannot distinguish with the usual area. Yeah. And okay, so this is one thing, but okay, so then the next I want to explain some more, since we already discussed instant counting, so it may be possible to discuss the topological vertex formalism to calculate the topological string derivation of the Necklace function. For the supergroup. Yeah, okay, so this is mostly done with Yuji Sugimoto. My paper is microoperator. And actually, building block of this topological vertex is that, okay, so if you have such vertex, so this building block is just this trivalent vertices. And this describes the local C3 part of this calabial. And so we have, if you want, oh, sorry. So in general, so Q1, Q2 here. And I'm not going to use a convention. to the standard convention. So we use typically the Q and T parameter, but in this case, the correspondence is something like this. Okay. Okay, so then the idea for the supergroup realization is the following. Since for the supergroup case, so we should assign a negative epsilon 1,2 parameter. I mean, so relative to the positive node, so we should assign some minus epsilon 1,2. So in that case, so we should have for the negative node. So we should flip this Q12 parameter, omega background parameter, to inverse. Then from this point of view, so we may introduce a negative vertex or the anti-vertex. The anti-negative, okay, doesn't matter in this case, since we are talking about some topological stuff. So essentially equivalent, but anyway, so we assign negative vertex, for example, Q1 inverse and the Q2 here. So if we want, okay, let me use a different color here. Okay, how to use this is the following. So if we want so we may think about this kind of the combination. The reason is that if you think about the T-duality, so this configuration is expected to be dual to such single positive, single negative brane configuration. Okay, and okay, so then the remaining calculation is essentially same as the usual. So then if you want, you can see the agreement between this topological string calculation and the instanton counting calculation. But okay, so let me give it a quick remark about at this point, the framing, okay, how to assign a framing factor is a bit tricky. So actually, we don't know the a priori definition of framing factor. So in that sense, okay, precisely speaking, in my previous paper, so we just checked the super conformal situation where we don't need to assign any framing factor. So then in that case, we can see the agreement between, I mean, the cross-partition function and this vertex calculation. And okay, so let me give it a one more nice interpretation for this anti-vertex. So if you think about the undefined slice, undefined limit. So in my convention, this is a Q1, Q2 equal 1. So if you want Q equal T in the standard convention. So in this case, okay, so we have such a vertex. So Q. And actually, so this is equivalent to the CQ inverse here. So this is actually anti-vertex. Okay, so we need some framing, but some extra factor. But essentially, so so this anti-vertex is same as the usual vertex, but the orientation is actually different. So if you want to, you can easily see this because if you, okay, original topological vertex is written using a Schur function. And then if you flip all the Q parameter to Q inverse, so basically you get the transposition of the partition. And then that gives you the different orientation here. So this orientation argument is actually consistent with the other argument. For example, the okay, so then let me remark the corner vertex operator algebra perspective. Actually, so this is based on the Milo's paper. Especially there, okay, so for example, if you think about this kind of singularity, okay, the angle is not matter here, but okay, it's a bit tricky. Okay, so if you think about such kind of the geometry and then N, so you can get So this GLN algebra. And if you want okay, so this is n plus n minus. So this is associated with GN plus / n minus algebra. Yeah, so this was discussed in Miro's paper. And from this point, okay, so actually, so this is interpreted as such web diagram. And using this flipping argument of this negative vertex, so this is actually equivalent to, okay, it's a bit difficult to do, but so having okay, so since okay, the tension balancing condition is a bit not obvious, but so we have a positive and a negative branes here. So from this point of view, if you flip the omega background parameter here, so this is okay. In this case, so we can this is reduced to the standard vertex, but with a different orientation. So then it may describe the supergroup structure like this. But so the just a quick remark is that this kind of argument is only possible for the undefined slice. So of course we can discuss a similar undefined anti-vertex, negative vertex, but in that case we don't have such kind of nice property. So this is a very peculiar property for this undefined limit. And of course, this is this is also related to the some other argument, like if you want, so this has a similar interpretation as a Sokayot-Witten realization or the Mihailov-Witten of this supergroup swap. Or the supergroup generalization is so if you think about NS5, so for example, these three branes. So then in this case, so this is for the N-4 theory with a specific boundary condition. And then at the boundary, so we may have the Chern-Simons theory. But if you generalize this, so okay, so N plus and minus here. So both branes are usual branes, but using this orientation flipping argument, it may be possible to interpret this as a configuration N plus with negative branes here.
Except
so actually,
the former thing clearly makes sense, and the latter thing more likely doesn't, right? So, and if you say that it's equivalent in calculation, then I will use the left side because the left side clearly does make sense. And is the correct, I think, realization of supergroup in string theory rather than the right.
Yes. So, okay, the point is that, okay, especially if you think about the undefined slice, so this anti-vertex formalism is actually produced, I mean, consistent with this configuration, only using a positive branes. Yeah, so actually, so what happened for the undefined case? I mean, what is the interpretation is not yet clear, but yeah, at least for the undefined slice, so we have such kind of realization. Okay, so okay, now it's actually that almost 2 hours, but so okay, so let me give you the final point. It's very quickly explain the final point. Okay, so let me explain some connection to the defect realization of the supergroup theory. supergroup structure. So based on this work with Fabrizio, appeared in the last Friday. So the idea is following. So actually, so this supergroup theory may have a lot of the issues, but actually, so this gives you the effective description of intersecting defects. So the idea is following. So for example, in this perspective, so we can impose a codimension 2 defect. And from this brain picture, for example, okay, we have several possibilities, but let's think about this so-called Higgsing trick, root of Higgs branch technique. So originally we have such kind of stuff, but if you tune mass parameter and Coulomb moduli parameter, so we can go to the Higgs branch description. Okay, so this is a well-known picture, and more, detailed structure. For example, if you think about what happened, okay, how to interpret this from the Nekrasov-Partition function is, for example, if you have omega deformation parameter, so you should equate this Coulomb moduli parameter and the mass parameter. Okay, so let's think about just a rank 1 case for simplicity. So this is a very classical picture. No omega deformation. But if you have omega deformation, it's possible to think about, for example, n epsilon 1, for example. So it's known that if you tune the parameter like this, so we have some truncation of the instanton configuration. So in this case, so we have some Young diagrams, but you have some configuration, like originally, so instanton configuration is parameterized by this arbitrary partition. But in this case, so we have the utmost n row constraint. Oh, sorry. So we have this kind of constraint if you have such parameter tuning. So this is explaining and describing some trapped instanton, which is interpreted as a vortex, which is a codimension 2 defect in this case. But now, okay, so now we have 2 deformation parameters. So it may be possible to turn on another parameter, for example. And we have a similar constraint on the instanton configuration. So in this case, we have such thing. But we have some constraint like this. And then instanton cannot go beyond this cross box. And instanton, okay, this Young diagram or partition must be living on this region. So this actually suggests the connection to the supergroup. Actually, so for example, the previous one. So since we have at most n rows, so it may be possible to interpret this configuration, parameterize an SUN representation. And the right-hand side, so if you have such, okay, it is sometimes called a fat hook diagram. So this actually parameterizes the SUN/n representation. And this configuration is sometimes called a pit condition due to this Bernstein-Peltier model. And this configuration is also called the fat hook representation. So anyway, so this structure suggests that if you think about if you turn on this both epsilon 1, 2 parameters, I mean, if you tune the Coulomb modular parameter and the mass parameter using both epsilon 1, 2 parameter, so it may be possible to connect some supergroup structures. And actually, so on this side, so this is actually trapped instanton, and actually this has a description of the vortex. And the right-hand side, so this may be interpreted as intersecting defect. So especially, so we have a C, if you want epsilon 1 plane and C epsilon 2 plane. So it depends on which dimension you think about in the beginning. So if you start with a 4D, so we have an intersecting defect like this, and then having a single point. But if you start with a 5D theory, compact or circle, so intersecting defects, of course, I'm living in S1. So the possible connection to the supergroup structure is actually found following. So, okay, this is sometimes called a 4D, 2D correspondence, or the natural analogous thing is discussed also for the 3D, 5D. So let's think about okay, let me use this K-theoretic, 5D instanton convention. This is about the same for the 2D. Yeah, I think in this Berkeley, it's better to mention this is a triarity. So, okay, the structure is following. So we have 5D theory, but this is not this is the usual non-supergroup theory. And the partition function, the closed partition function, is giving us all the possible partition Young diagram. And if you impose this this condition, Higgs-sink condition, so you may have this 3D theory description, but for the moment, so we have a Higgs branch description, and the partition function is actually given by the some vortex sum. Okay, so for the generic Higgs-sink, so it's not interpreted as a vortex, but anyway, so we have some restriction on the partition sum here. So this is interpreted as some Higgs branch expression of the 3D theory or intersecting defect theory. Okay, so this is a Higgs branch description, but of course, so we can have a Coulomb branch expression. And in this case, this is actually replaced with some quantum integral. And actually the residue calculus gives you this Higgs branch expression. So in this way, so we can get what is this 3D partition function from this generic Higgs-sink. And actually, so this Coulomb branch formula. So we get the Coulomb branch formula. For example, if you think about the generic n/m Higgs-sink, so this is a Coulomb branch parameter, and then we have this kind of following matrix model like expression. Okay, let me explain the convention accordingly. So actually, so this delta is called a McDonald measure. Okay. So the point is that so this has a Q parameter. So this is related. Okay, now we are now talking about the CQ plane theory, and this T parameter is interpreted as an adjoint mass from this point of view. But now we are talking about both CQ plane and CT plane. So we have both this expression. So QT and the TQ here. So actually, so this structure is this. Okay, so this is not the end, but so we have several additional contribution. But actually, this measure is known as a measure for the super-Macdonald polynomial. Super-Macdonald. Okay. Okay, from this point of view, if you think about this generic fixing, having CQ plane, CT plane, so we have such a super-Macdonald measure. So this suggests a connection to the supergroup structure, actually. And okay, so if you want if you think about so the rational limit.
I'm afraid I will need to go because I have to pick up my son. So
okay, so
we can cut this a little bit, summarize this. I really honestly need to go. So
yeah, okay. So yeah, this is just the point. And if you think about the generic fixing, so we may think, okay, so this is the Patron function of the intersecting plane. And the point is that if you think about, okay, so if you see this structure of this intersecting plane Patron function, so this actually having a supergroup structure. So in that sense, okay, the starting point is not a supergroup, but if you think about some complicated defect configuration, so we may have a supergroup. And in that sense, a supergroup is giving some effective description of some intersecting defect. So this is a story from the 5D, 3D, but so we can have a similar argument for the 8D, 4D. So 8D theory is known as the so-called gauge origami by the Nikita. And then we may have a similar structure for the higher structures, higher dimensions. So yeah, basically this is so punchline. And then so yes, so actually, so we can also discuss some BPS CFT or gauge integral, okay, gauge weight correspondence. But so yeah, I think it's nice timing to stop there, concluding that talk here. Okay, yeah, thank you for the attention.
Thank you very much.
Yes, thank you very much.
That's fair.
Thank you. So are there more questions?
Okay, then let's thank Taro again.
Okay, thank you very much.
Thank you. Bye, everyone.
Bye.